All right, well, let me try another video solution as you guys are working on this. Looks like somebody's kind of struggling with the number 113, and it's again in the challenging problems from the harder book. So let's see why it's here. So number 113 says the position of a particle moving along the x-axis varies according to this equation. X equals 5t squared minus 4t cubed. All right. Now, let me pause right there and just maybe ask one of the standard questions you always want to ask yourself is this a constant acceleration problem? Because let me grab these equations I keep showing you. These are our 5 kinematic equations that are only valid for constant acceleration. So we want to really ask ourselves, do we have constant acceleration? And problems like this, it's a little bit harder to decide that because they're not telling us anything about acceleration, although they are related. So we can say a little bit about the acceleration. And we will see that this is not a constant acceleration. And we know that, let me come back to these equations. See, these equations are saying if you had constant acceleration, the equation for position would be quadratic in time. Of course, velocity would be linear in time. So we had a problem earlier on where they gave us velocity and it was not linear, so it was not constant acceleration. In this one, they're giving us the equation for position and it's not quadratic. See, it's cubic. They give us cubic. And so this does not fit this pattern. So this is the pattern you derive when you have constant acceleration, and that's not what we have. So this would not be constant acceleration. So that's a dead giveaway. That also means I will not use these equations. I will go back to just the basic idea of how velocity and position and acceleration are all related. Okay. All right. So reading the question, it says find, A, the velocity and the acceleration of the particles as function of time. So I'm going to go ahead here, and since I have a position, why don't I take its derivative, and that will give me velocity. So velocity is the derivative of position. So that means take the derivative. And it looks like I've got a 5t squared minus 4t cubed. And so we can separate that into its two pieces. The 5t squared and the 4t cubed. And then we can pull constants out in front. Let me do it for this one too. Pull the 4 out in front. And so you're saying, what's the derivative of t squared? Now, I don't think I saved that piece of paper. Here it is. Digging in my trash pile here. But earlier on, I was doing a problem with the calculus and pointing out that this is how you take a derivative of a power function, and this is how you take the antiderivative of a power function. And so we're not going to do too hard of derivatives or integrals. They're going to be these power functions, and so that's what I have here. Now, this problem in particular, I forget which number it was, but I want to say 80, but it does have an exception when n equals -1, and that's when you get the natural log. So I'll throw that back out there. But I'm not doing an antiderivative, I'm just doing a derivative. So I'll follow this pattern where the exponent comes down in front and the power is reduced by 1. Okay, so here, t squared would become just 2t. And t cubed would become 3t squared. Now, if I simplify it, 5 times 2 is 10. So we got 10t. And 4 times 3 is 12t squared. And so there is the equation for velocity. And I'll put a little box for the equation of position, velocity. And then, of course, the other part of this was to find the acceleration. And so looking at our little calculus here, the acceleration is derivative of velocity. So let me take the derivative again. And so 10t minus 12t squared. And again, you can separate this into the two pieces. So this is the derivative of 10t minus the derivative of 12t squared. And if you'll let me do 2 steps here, I'm going to pull the 10 out in front and then take the derivative of the t, which means bring down the power 1 and reduce the exponent by 1. And of course, t to the 0 is a 1. So 10 times 1 times 1 is just 10. And then minus, and if you kind of let me do 2 steps here also, I'm going to pull the 12 out in front. And then the t squared means you pull the 2 down and reduce the exponent by 1. So that just becomes 2t. And if we simplify it, 12 times 2 is 24t. And there would be the equation for the acceleration. And notice it changes with time. And so there fits what we said earlier. This is not a constant acceleration problem. If this was raised only to a power of 2, then we would have got a constant down here after we took the derivative twice. But if it's any other power, which it is, other than 2, you won't get a constant down here. And we didn't. So there's more of our evidence that it's not a constant acceleration problem. Okay, so that's A. B is not too tricky. It just says find the velocity and the acceleration at 2 seconds. Okay, so velocity would be, and I just got to put in my 2 seconds. So it would be 10 times 2 minus 12 times 2 squared. So 10 times 2 is a 20. And then this 2 squared would be a 4. 4 times a 12 is a 48. And so we get a velocity of negative 28. So there'd be a number for you. Acceleration, same idea. And we're just going to put in the 2 seconds because it says find the acceleration and the velocity at 2 seconds. And so this becomes 10 minus 48. And so that becomes negative 38. Okay. So B is just kind of a plug and chug and using our derivatives here. C says the time at which the position is a maximum. Ooh. Now, this might be worth thinking about. It's going to take us back to our algebra and calculus class. But they'd give us an equation for position. And if you remember doing graphs like this, when you have power functions, focus your attention on the highest one. Because the highest power is going to dominate for either big times or negative. And it sounds weird talking about negative times, so we'll add more to that. But if this was just an x-axis, we could have positives and negatives. So this dominates. And so if you remember a graph that is y equals x cubed would look something like this. Okay. And we have a cube, although we have it multiplied by a 4, and we also have a negative of it. So everything's going to be reversed. So reversing everything and multiplying by 4 would make it a little steeper because we're multiplied by 4 and switch it over. But then we're doing this thing. We're putting a parabola. That's what gives it that little kink here. So this graph of, whoops, I should have put position versus time, would come down here, have what we call a double root here, come up and pass through a 0 there, and then head on down to negative infinity. Okay? Now, if we limit our discussion to time greater than or equal to 0, then we don't have to really focus on this downward negative one. This is really then saying we start at 0 and we go increase our distance up to some maximum, then we decrease it coming back to 0, and then our position actually begins to go negative. And of course, now the question maybe makes more sense because they said the time at which the position is the maximum. So there is some greatest maximum value if you don't worry about negative times here. And so I'm pretty sure they're talking about, all right, this is the equation of the position starting at time equals to 0 and going forward. So not worrying about the negative values of time. This right here is its maximum. In fact, if you go down and read question E, it says, what is this maximum position? So why don't I answer C and E together here? Because the C is at what time is it at this maximum, and E is then what is the value of that maximum. Now, this again is really kind of a calculus question. You might remember maximizing functions. Maximizing functions says take the derivative and set it equal to 0. Okay. Well, we already did take the derivative. We called it velocity. We did it here. And of course, setting it equals to 0 means that it moved up with a positive velocity until it came to 0, and then it went back down. So that's why its highest point is at y equals to 0, and that's why it fits what we did in a calculus class by looking for a maximum function. Maximum function says set the derivative equal to 0. Now, I should apologize. I said maximum, but what it gives us is really the slope when it's 0, and that would give us maximum or minimums. So this really is the slope of this curve. And so when we arc up at the top, we have a slope of 0. So that's why it's going to get maximums. But we also, minimums have a slope of 0. So taking the derivative and set it equaling to 0 either gives you minimums or maximums. And that makes sense. But let's solve it now. So if I factor out a t, I would have 10 minus 12t equals 0. And then I would say, well, if two things multiplied together is equals to 0, either the first one is equal to 0 or the second one is equal to 0. And if you come back to the graph, when t is 0, right here, we do get a slope of 0. That's where we get the minimum. Or at least maybe I should call it a local minimum, because then it shoots on off and gets lower and 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 lower. So mathematically, there is no limit to the minimum. I mean, there is no absolute minimum. But there's a local one where it goes down to 0, goes up back to positive, and then takes off to go down. So that's the one that, of course, shows up when we take a derivative, but it's a minimum. Whereas this one would be really what we want right there. That's a maximum. So I'll put the 12t over on the right, and then I'll take the 10 and divide it by 12, which reduces to 5 over 6, which, if I get a fraction here, 5 over 6 is 8, and 3 is repeating. And so there is the answer to C, which C says time, right? The time at which the position is at its maximum. But I can answer E now by just plugging in the value for that time. And then calculating what is its position. So now that we know at what moment in time, we can just calculate its position. So this would be 5 times, and I'm just going to take my last answer and hit square. So that's that piece. Then I'll go minus 4 times, and again, last answer. This time I will cube it and just hit enter. And so it looks like 1.16 meters. And so this back here to our picture saying it goes up to 1.16 meters and then starts to come back down to 0 and then actually goes negative on down. All right, so the only thing we're missing now is D, since I jumped over to get E, which what is its maximum position. D says the time at which the velocity is 0. No. The time at which the velocity is 0. Oh, I did that. That one is throwing me off here. The time at which the velocity is 0. Well, that is the derivative of where you get the maximum function. Maybe that's the point of the problem. Okay, so the point of the problem maybe is to say, look, this when the velocity is 0, this is where it is going to get its maximums. Yeah. Well, that was kind of boring. Okay. But I guess that was the point, that when you maximize a function, you take its derivative and set it equal to 0. But taking its derivative is the velocity, so setting the velocity equal to 0 would be that time when you get those maximums. Huh. All right, so C and D are really the same question. And I guess getting you to try to maybe tie your math together with your physics. That one, I don't know if I really see the benefit of that question. All right. Well, done with that question. Hopefully that helps. Bye now.